All right, so now let's talk about probably the most, or one of the most important reactions in organic chemistry, and this is the Diels-Alder reaction. And I hope I'm saying that right. I get a lot of criticism because of my accents, but this is so important because what you're doing with this is you're forming a 6-membered ring. So I'm just going to make some notes, or just not necessarily that, but let's just make some notes about everything that happens in a Diels-Alder reaction. The most important thing is you create a 6-membered ring. Every time you do this, you're getting that. Think of all the reactions you can do with that. So of course, this is something that's going to be pretty highly valued. What you have to do usually is you have to add heat to make sure that you're starting off with a S-cis alkene. Hopefully that's or S-cis-diene, sorry. It is an alkene, but it's a diene to be more specific. You're going to have 3 pi bonds. This is insane. 3 pi bonds will be broken, and 2 new carbon-carbon sigma bonds will form. This is a concerted reaction. What do I mean whenever I say concerted? Well, what that means is that all bonds are broken and formed at the same place. So I'm going to say breaking and forming take place at the same time. Forming at the same time. And then the last thing that I want to include, it's not superbly a requirement, but it's something that really helps, is that when you have an alkene, it's going to act as something called a dienophile. We'll talk about this stuff later. And a carbonyl group, I'm going to switch colors just to drive home that point. And a carbonyl group attached to it, that's a carbonyl group. The carbonyl here makes it much, much faster. So it's a catalyst. Catalyst for this reaction. Why is it a good catalyst to have for this reaction? Because it's really good at being electron withdrawing. It's going to pull those electrons out of place. It's going to generate a slightly positive and slightly negative and slightly positive ends. This will make sense when we draw out the mechanism. But before we divulge into that, I just wanted to make sure that we were understanding that these things happen. These things are really important to the Diels-Alder reaction. Okay, so with that being said, let's go ahead and just draw a generalized mechanism for a Diels-Alder reaction. So I'm going to go ahead and just rewrite that up there. Diels-Alder reaction. So there's always going to be certain reagents in a Diels-Alder reaction. I'm going to draw a really simplified one. You have some type of a conjugated diene, and it's going to react, I don't know why I have that there. It's going to react with another alkene, and this reaction can proceed, but 9 times out of 10, 90% of the time, you want a carbonyl group of some kind attached to it because it makes the thing a lot faster. I go ahead and add some heat. That's my symbol for heat. And what I'm going to get out of this is one of these bad boys. There, and there. So this is kind of confusing when you think about it. Let me draw the electron pushing arrows for how this works. So because this is electron withdrawing over here, you're going to have highly reactive electrons in this substance. I should have clarified that this is called, these 2 substituents here are called, the alkene group is called the dienophile. And then our S-cis, it has to be S-cis. This has to be S-cis. This can be whatever, but this has to be S-cis. Is called your diene. Robert, your spelling teacher would be mad. It's called my diene. So let me draw the electron pushing arrows for this because it kind of does get confusing. So the first thing that happens is that the pi bond here comes after this carbon. That should be a little bit like, what the hell? Well, and this is the point in organic chemistry to where the whole positive and negative thing, because up until now, literally everything you've learned in chemistry is nothing but positive and negative coming together. But this is where we start running things under kind of obscure, extreme reaction conditions to force things to do our bidding. Kind of like it's a very forced reaction. We have to add a lot of heat to do this. We have to add these carbonyl groups to be electron withdrawing. But the pi bonds in this alkene attack this carbon atom. And then the pi bonds from here are going to migrate between the two. And in doing that, it's going to form a bond there. So obviously I have to get rid of something. Well, this just lost its electrons. As this loses its electrons, these electrons start to come and attach themselves to him. This would be really, really difficult if not for a crap ton of heat that we're putting into our reaction and the carbonyl group that we have. But it's what we form is, and I wish my book would be more specific in stating how efficient this reaction is, because I don't know. But what we form is a 6-membered ring that is attached to it, and this is all in one concerted reaction here. Now in this, we're not even going to get mixtures. So think about how amazing this reaction is. Think about all the things that you can do with a 6-membered ring, all the drugs that you can make, all of the stuff that you can synthesize from this. This is a very important reaction. So that's the generalized overview of our reaction. The next thing I wanted to talk about, though, for this at least, is the stereospecificity of it. And I feel like sterics is kind of overrated, but stereospecificity of DielsAlder. So with anything that you have, with any reaction that you have, if you have a cis reactant, you'll get cis products. And if you have, I could say the same thing with trans. If you have trans reactants, you're going to get trans products. What I mean whenever I'm saying this, so say for example I have let's just say here's my diene here, and I go ahead and react that with just trying to think of something that I could use that's an alkene here, but it has a carbonyl group attached there and a carbonyl group attached there. So these carbonyls here are going to react with each other. They're cis in conformation. It's kind of getting ugly. Let me see if I can't clear that up. Let's erase that. I don't know why that's there. Let's erase this up here. Okay. So remember, the only thing that the diene has to be S-cis always. So S-cis diene. You can't, that's undisputable, that this reaction won't proceed. But this right here, though, this is a trans alkene. This is a trans alkene. So when we do this reaction, when we do this event, what type of a product are we going to get? Well, we're going to get a trans product. That's a given, no matter what, because we have a trans reaction over here. So I could draw out the electron pushing arrows. I mean, I guess I might as well go ahead and draw them there, 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 but I prefer to just kind of literally draw the little lines connecting each and every one of these. So when I draw my products of this reaction, if I could find the color, there she goes. I'm going to go ahead and just draw my 6-membered ring. That's not any different. We have a pi bond there. That's not any different. But what about these two substituents, these two groups here? Well, the first one is going to be kind of a wedged conformation there. There, and then the second one is going to be dashed. This is a really bad drawing. I know, but if you can hopefully see that those are conformations there. But this is obviously, what is this? This is trans. So I also need to label that this is plus enantiomer. And the same thing would be the case if this was a cis product. I would have a cis reactant, I would have a cis product plus an enantiomer, or if it was symmetrical, it'd be a meso compound, but that's kind of rare. Okay, so the next thing that I wanted to talk about, though, is and this is kind of the most confusing thing for a lot of students, and it was confusing for myself as well, is the briged bicyclic products. And I'll explain what that means in a second. So say, for example, in most reactions are going to proceed with this type of a generalized mechanism of a things that you're going to get is called a briged bicyclic product, and this usually results whenever you have a ring as your diene. Now this is in the S-cis conformation, and here we have our just generic diene. Of course we're going to have to use this under extreme heat conditions because there's no carbonyl attached to it, but the first thing that you want to do is label or number your carbons. So I'm going to say right here, I have right here, this is carbon 1. Right here I have carbon 2. Right here I have carbon 3. Carbon 3. Right here I have carbon 4. And over here I have carbon 5. On this end I have carbon 6. And on this end I have carbon 7. So I go ahead and just draw this out like this is going to be a generic reaction here. This I'm just going to go ahead and just draw like little dots there to show that it's reacting with that. So these two react under a DielsAlder reaction. I'm just going to go ahead and write DA for DielsAlder reaction. And here's how I'm supposed to draw the products, or here's how you're supposed to draw the products. I kind of take issue with this because it's the textbook, but I mean it's their book. They can do it however the hell they want. So your product looks something like this in a three-dimensional conformation. At least we draw it looking like this. There. There, and I'll go ahead and switch colors to show that it's the there, there. There's that there. Okay, so what the hell does this mean? Well, I'm just going to go ahead and go back to circling all of these, and numbering my carbons will definitely help me remember where I'm at in this. So this right here is carbon number 1 with that. This right here is carbon number 2 with that. This right here is carbon number 3 with that. This up here is the pointy part up here, so this is carbon number 4 with that. And this right here is carbon number 5 with that. This right here is carbon number 6, and this is carbon number 7. Now, I'm not numbering these in terms of IUPAC nomenclature. I'm just numbering these so that I don't get lost whenever I'm drawing out my products. And there's two I guess, positions that you can have as far as substituents goes. One of them is the exo, which is out like this, and the other one is the endo. And this is what the book says. This is what the Grzinski-Smith textbook says, and I fucking hate it. Why do I hate it so much? Because this is the endo substituent. This is where the more stable, the carbonyl substituents are going to go. And this, from the way that this diagram looks, this makes it look like it's a axial position. This is, I just want to be very clear that this is not axial position here. If you want to draw the way that David von Bronken from UC Irving is, yes, I'm in the open course right now, but the way that he draws it is kind of as this different. He draws it drastically different, but I like the way that he draws it. He draws it basically the same way, and this is a horrible drawing. You should check out his videos. Put a link in the description if you would like. But he draws them like this, going down in this direction here. And on the top here we have that, and there that. This is the exo substituent for his stuff, and this is the endo. And I like that because in this we can see the endo substituent, it's more stable with that way because it's in the equatorial plane rather than the axial plane. But just know that this is the same diagram, it's just drawing this, I think, upside down, if you could kind of imagine it being flipped. But this is what the book says, so I have to go with that. But the endo substituent goes there, and this is not axial. But this is kind of confusing and really difficult to draw. If I were to draw the what this would look like in the Lewis structure, this is a three-dimensional structure form, but this is kind of what the Lewis structure of this would look like. It would give us something kind of along the lines of this. So you would have a 6-membered ring here, and going across that 6-membered ring, give it dashed, or not dashed, but yeah, make it look like a wedge so that you can see that it's coming out of the plane. This is also a Lewis example of this product here. I want to make a note that on the end of that, I did not include the pi bond that is formed between carbon 1 and 2. I was so lost up in my criticism of the endo-exo substituent things that I forgot to mention that, of course, there is a pi bond, and you need to draw that pi bond that's formed between 1 and 2 in a Diels-Alder reaction that gives us a bridged bicyclic product.